Lesson 321, summing it up with sigma. So the goal today is to be able to recognize and calculate sums by using sigma notation. So we're going to work through some new math notation today. Math is all about patterns. So today we're going to look at how to represent sums of sequences and look at different patterns. So taking a look at problem 85, we want to evaluate the sum of this sequence. So if we start writing out each term in the sequence, 0.01 times 2 plus 1.7, 0.01 times 3 plus 1.7, 0.01 times 4 plus 1.7, all the way to 0.01 times 20 plus 1.7. Evaluating these on a calculator, and adding up each term, we get 34.39. Now, that takes a while to do, to write out and add up all of those terms. So if you have a sequence of 5 or 10 terms, that's doable by hand. But what if we have a sequence of 100 terms or 1,000 terms? We need to find a pattern and a rule to be able to add up those sequences. So first, looking at sequence notation. If you're given 4 values for n and the rule for the sequence, first you're going to evaluate when n equals 0, and then when n equals 1, when n equals 2, and lastly, when n equals 3. So adding up those 4 terms in the sequence, I have 15.75. Now, what if we did the exact same thing, except this time we started when n equals 1? So we're going to have 3.125 plus 4.5 plus 6.125 plus evaluating the term when n is 4, which gives me an 8, and adding up those terms in the sequence, I get 21.75. So what are the similarities and what are the differences? It's the same pattern, but a different starting value. So we have to be very careful at looking where the starting value is in our sequence when we're creating the sum of the sequence. Notation that we're going to use for calculating the sum of a sequence is called sigma notation, and it's from the Greek letter sigma. Another word for sigma notation is summation notation. And it's a shorthand way to write out the pattern for a sequence. So if I want to add up 4 terms in the sequence with the pattern n squared, I'm going to put my starting value at the bottom of the sigma letter and my ending value at the top. So n in this sequence goes from 1 to 3, and I'm evaluating n squared when n equals 1, n equals 2, and n equals 3. So the way you read sigma notation is this symbol is read the sum of n squared from n equaling 1 to 3. And when you add up the terms in that sequence, you have a value of 14. So n squared is the argument of the summation. N is the index, and n can only be integer values. So if I'm given the argument 2 to the j power, and my index is j equaling 3 to 6, I'm evaluating this argument when j is 3, when j is 4, when j is 5, and when j is 6. So I'm adding up the terms in this sequence to be a sum of 120. Looking at the argument in letter C, the argument is 16 times 1/2 to the k power, with k going from 1 to 5. So as I write out the terms in this sequence, I have the starting value when k is 1, when k is 2, when k is 3, when k is 4, up to and including when k is 5. So I'm adding up each term in this sequence to get a sum of 15.5. So we can do these by hand, or you can do them on your calculator. If you're using the calculator on the Chromebook, you're going to press the math button and 0. And your calculator will give you the summation symbol, and you can type in your argument, and then your index going from the starting value to the ending value. So what your calculator is doing in this case is taking your argument and adding it up when x equals 1, x equals 2, x equals 3, up until x is 10. And it is adding those terms together to get that solution. If you're not on your Chromebook, or you don't have access to a TI calculator, another option is using Desmos. And if you're going to go into Desmos, you can click on the Functions button, and then Miscellaneous. and then the summation button. And just like on your TI calculator, you will be given the summation symbol, and you can then type in your argument and tell it to go from, and in this case, it looks like Desmos put an N in there. So I'm going to make that match. So my argument is going to be 1 over n squared, n going from 1 to 10. So taking a look at problem 88 and checking Whelan's work, if this is my problem, my argument is p squared with an index going from 5 to 7. So the first term in this sequence is going to be 5 squared, the second term 6 squared, and the third term 7 squared, giving me a sum of 110. So this is not correct because the index can only be integer values. We can't have a 5.5 for p or a 6.5 for p. We're counting by 1 each time we increment the index. So if we have an interval between 2 and 3, including 2 and 3, and we want to break that into 5 equal segments. So if we want to calculate the length of each subsegment, I can do 3 minus 2 to get 1. And I'm dividing that into 5 equal segments. So the length of each segment is going to be 0.2. So my interval goes from 2 to 3, and each segment is 0.2 in length. So I have 1, 2, 3, 4, 5 equal segments. So looking at the left endpoints of each subsegment, my first segment has a left endpoint of 2. My second segment has a left endpoint of 2.2. My third segment has a left endpoint of 2.4. My fourth segment has a left endpoint of 2.6. And my fifth segment has a left endpoint of 2.8. So if I want to write an equation for this sequence, this is my first term, second term, third term, fourth term, fifth term, labeling the 5 different segments. And if you think back to algebra and geometry and algebra 2, where you were writing equations for arithmetic sequences, my common difference is 0.2. So I'm increasing by a value of 0.2 every time. And then you need the 0 term in your sequence. So in this case, I would have to go backwards to get the 0 term. So for my equation, I would have a starting value of 1.8. if I list the right endpoints of each subsegment, my first segment, second segment, third segment, fourth segment, and the right endpoint of my fifth segment, and I want to write an equation for this sequence, again, I'm incrementing by the same common difference, but my zero term in this case would be 2. So how are these related? They have the same common difference, but different starting values. So we really need to be concerned where we're starting our counting. Are you starting counting with 1 or are you starting counting with 0? Are you looking at the 0 term or the first term? So a series is the sum of the terms in a sequence. So if I want to express the sum using sigma notation, I have to make an argument and I have to figure out my index. So if I look at the common difference, I'm adding 0.4 each time. So I know I have a common difference of 0.4 n. But now if I want to express the sum of this sequence, if I'm going to use 3.6 as the 0 term, I need to make sure I start counting my n's at 0. And if 3.6 is the 0 term, I have 1, 2, 3, 5.2 is going to be the fourth index. So my index is going to go from 0 to 4. And my argument is 0.4n plus 3.6. So what changes would I make if I wanted to sum up this using the exact same argument? I could still say my 0 term is 3.6, but now I want to start counting at 1 and go to 5. So computing that sum on your calculator, you should get a value of 22. From part A. Let's put that in Desmos just to double check it. So if I go to Desmos, and again I'm going to click on Functions, Miscellaneous, Summation, and I'm going from 0 to 4, and my argument is 0.4 n, if I'm going to use n's. I could also use x's, the variable doesn't matter, plus 3.6 and And I don't get 22. That's why I wanted to double check that. Let's go back and do it by hand. So if I have 0.4 times 0 plus 3.6, 0.4 times 1 plus 3.6, 0.4 times 2 plus 3.6, 0.4 times 3 plus 3.6, and 0.4 times 4 plus 3.6. Adding those up, I do get 22. So let's go back and double check that on my calculator. And let's change these to x's. Let's see if this makes a difference in Desmos. All right, I'm going to have to go back and I'm going to double check on Desmos and I'm going to get back to you on that one. So as we wrap this up, for problem 91, suppose that we have this summation and we put this in sigma notation. So we're going from 0 stating that 3.6 is the 0 term. So why is this the argument? So we have a common difference of 0.4. And the 0 term is 3.6. So we have to decide how high are we counting. So what's the highest index? So if I take 0.4n plus 3.6 and set that equal to 23.6, n is equal to 50. So I'm counting from 0 to 50. So if I want to write this next sequence in sigma notation, I have a common difference of 0.2. And my 0 term, I'm going to start counting at 2.5. So I'm going to say n equals 0 to make that my 0 term. And looking to see how high I have to go as an index, I'm going to take my argument and set it equal to 22.5. N equals 100. So that's what my sigma notation is going to look like. So for practice on this, please complete complete these problems, bring your questions back to class and we will clear up any questions you have. Have a good night.